I guess good morning, everyone. I know I'm between you and lunch, so I'm going to keep things quick and snappy. So my name is Yan Cui. I'm an independent consultant where I work with clients from all around the world on how to solve business problems using serverless technologies. And as of last year, I'm also one of the AWS serverless heroes that focuses around helping the community adopt serverless and best practices. And I'm also working as a developer advocate for Lumigo, which is a company that's building a troubleshooting platform for serverless applications running on AWS Lambda. But long before all of that, I was working for a social network called Hubble, which you can think of as a mix of Instagram, Twitter, and Facebook. And it was there that I really learned a lot about what it takes to build and run a serverless application in production reliably. So when I joined Hubble, this social network, back in April 2016, I inherited something I guess many of you are familiar with, a very monolithic system with a few servers running on EC2. And then by, I guess, November that year, me and a very small team, we have pretty much moved the entire social network to run entirely on serverless technologies. And when you look at this, you may think, well, that just looks a lot more complicated. What are you guys thinking? Why do you do all that? The thing is, all that complexity you see already existed in the monolith. It's just that they were all hidden away inside your code. Until you actually peel away the cover, you're not going to see these complexities. So oftentimes, I actually find that with serverless, a lot of the complexity that you already had just gets lifted up into the surface. But before you do any sort of big undertaking, re-architecting, rewriting your application, a good starting point would be asking yourself, why? Why is this worth doing? Well, we were an early-age social network. We didn't have that many users. I think at the time, the platform had about 1 million users in total. But we did manage to get a few influencers from other platforms to join us. Emily, for example, was one of our top users. At the time when the whole platform had about 1 million users, she had about 50,000 or 60,000 followers. And like Emily, many of the social influencers, they would write a post on our platform to say, hey, guys, please come and vote on this post, and then at 10 o'clock, I'm going to announce a lucky winner for this beautiful designer handbag. So throughout the day, things are really calm, don't have much traffic, but at exactly 10 o'clock, we get this massive surge in traffic because everybody's come in to check whether or not they want Emily's handbag. And since we don't have any control of the different things that the influencers are doing on our platform, so this kind of makes my life difficult as an engineer in terms of provisioning enough resources to handle all these unpredictable spikes in traffic throughout the day. So what that translates to is that we end up having to run our EC2 cluster at a much lower utilization than we would like, and also to scale up a lot earlier than we would like as well. Because when you put the two things together, it means that we are spending a lot of money on resources for AWS that we're just not using. By my estimate, we're probably using maybe 5% of the CPU cycles that we actually pay for on our EC2 instances. And at the time, every time we do a deployment to production, it requires the whole app to go down and then back up, and takes about 30 minutes as well, which nowadays is clearly not good enough. And features was taking months to develop. And one of my favorite speakers, Dan North, once said that the lead time to someone saying thank you is the only reputational metric that matters to us. And it's a message that really resonated with me and has stuck with me ever since. And as engineers, doesn't matter how much work you've done, until your code is actually running in production and serving value to your users, as far as the users are concerned, you haven't done anything at all. So going back to why do we have that whole undertaking to move to serverless, first and foremost, we want to deliver better user experience to our users. And as a team, we want to be able to deliver values faster as well. And as a company, we also want to be more smart about how we're spending money on AWS to be more cost efficient. I think the goal should never be to cut costs per se. If something is delivering a lot of value, I'm really happy to pay a lot of money for it. But what I'm not happy about is to spend money on things that are just going to waste. I want to be more efficient and want to think about it in terms of the return on investment for what we're spending. So that's the why. In terms of how do we deliver on these goals that we have, first, we need to decide what a good architecture would look like for us as a team based on the skills that we have. So we sat down, had a discussion, and we decided that we want deployments to be small, to be fast, no downtime, and we also don't want to be in a situation where we have to do lockstep deployment with the mobile and the web teams because of the sheer amount of coordination and stress that's involved there. And we want features to be loosely coupled through messaging and for them to be independently deployable as well. And we also want to be more efficient in terms of our AWS cost. We want to minimize the amount of money that we spend on resources that we're not using. And we also want to minimize the amount of effort that we have to spend and time that we have to spend as an engineering team to look after our infrastructure. As far as I'm concerned, infrastructure should work for me, and they should just work, not the other way around. I don't want to spend my time just babysitting my infrastructure to make sure that it's still working. And we also want to reduce the amount of technical mess that we have as well in the system, and that's a very conscious choice of wording. You see, when people talk about technical debt, it implies that at some point, someone is taking a conscious design decision to take a shortcut so they can ship earlier. A lot of the problem that we found was not that, it was just really badly done the implementation. And whilst we address all this technical mess that we inherited, we don't want to take 6 months out and not deliver anything. If anything, we actually want to deliver value to our customers faster and quicker than ever before. So in terms of how do we want to achieve our goal, we decided on a course towards a microservice architecture, building a system that's driven by events and using serverless technology as the primary force to deliver our implementation. And this talk is about some of the things that we actually managed to do very, very quickly. If this looks familiar, then you probably have read the book by Simon Sinek, Start With Why. If you haven't, definitely go and read it. It's excellent. So by the time we finished the whole transformation, we had over almost 200 Lambda functions running in production. And even though cost wasn't the primary reason why we did any of this work, we did find a really healthy dose of cost saving on Lambda compared to the amount of money that we were spending on EC2 because of the amount of resources that we were paying for and not using. But more importantly for me, we managed to increase the velocity massively without having to hire lots of engineers. We keep the team at the same size, but we went from doing a production deployment every, 4 to 6 times a month to easily averaging over 80 to 100 deployments to production every month. And sometimes there were quite a few incidents whereby features and enhancements were discussed, implemented, tested, and shipped all in the same day. Between us deciding that Lambda is a good fit for the direction that we're moving towards to having that first function running in production, we have to be diligent. We have to know how that we're actually able to run this in production reliably. So we had to answer questions around how do you do CI/CD, what about testing all these cloud-hosted functions, what about logging, monitoring, alerting, and so on. And as our system expanded to include more and more functions, many of which have different interdependencies, we also had to answer questions around how do we do tracing in this world, what about config management and security. All these things are very, very important to talk about, which is why I also put together a video course for Manning to cover all this topic. But today, I want to talk about some of the things that we did do in terms of evolving our platform and also to deliver features along the way as well. One of the first things we did, and probably the most important thing we did, was that we made sure that our legacy system is publishing all state changes as events to a Kinesis stream, a real-time stream of events that we can process. And these events are a great way it's great for composability and allows us to build our systems in a very loosely coupled way. And Lambda is a glue that allows us to connect all these different services together. So in this world, we have our Kinesis stream as a sink, and we have a bunch of different microservices, many of which are implemented with API Gateway and Lambda. And whenever they do something interesting to change the state of the user or the system as a whole, they will publish those as events into Kinesis so that other microservices can react to those events with Lambda. And maybe they will do their own thing. Maybe some would synchronize data by taking a copy of data they're interested in and saving them into their own DynamoDB table. Or maybe they want to publish some real-time update to the customer via IoT messaging broker. And whenever these other microservices make some state changes, that they will also publish them as events back into the stream so that other systems can then react to them and so on and so forth. So events is a great way for you to build your system in a really loosely coupled way, whereby once you identify the boundary context for your microservices, instead of having different Microservices cross the boundary context and talk to each other directly, and end up in a world whereby you have all these interdependencies, so that if one service goes down, anything else that depends on that also goes down, and you end up with what we call cascade failures in the distributed systems. A lot of time, you can decouple the systems by event through some kind of a stream or a queue. This idea is, of course, not new with serverless. It's been around for a very, very long time. Databases has the same idea with transaction logs. And in the distributed systems world, there's also this idea of event streaming. And a friend of mine has been trying to write a book about this topic for a very, very long time. I don't think he's ever finished. So I love building systems with events. I love this whole event-driven architecture, and it's definitely my preferred way of building systems nowadays, but it's by no means a silver bullet. It solves some of the problems that comes with building systems, but it also has got its own baggage and complexity as well. For one of the things that you find is that when you're building all these event-driven systems is that you have all these different microservices. They are pushing events into the stream, but then they also at the same time consuming events from the same stream. And then say if you want to update the contract for one particular event, how do you make sure that you don't accidentally break some other system somewhere else that depends on the event that you're publishing? One of the things that I've done up to now, I guess, is mostly depending on discipline and communication, but it's, of course, far from bulletproof. And whilst it's still very much early days, I think it's worth for you to sort of investigate the async API spec, which allows you to create a stronger contract around your messaging. And then you can maybe do some consumer-driven testing around those contracts as well to make sure whenever you do an update, you're not going to break someone else who is depending on your message. Another common mistake I find is that when you try to implement a workflow inside a particular bounded context using events, and one of the problems with this is that you're now inviting complexity around the logging and monitoring and doing reporting at the end-to-end for the entire workflow, because the workflow itself doesn't exist as a standalone concept anywhere in your domain, but only as a sum of a set of loosely connected parts. And the only time when the workflow so comes together as a whole is inside your mind, inside the mental model that you have about how the system actually works. So when it comes to implementing workflows, my preferred approach is to actually use a workflow engine, such as Amazon's step functions, which allows you to also visualize your workflow, which I think is a great way when you're designing a system with contract first with, say, the product team, who may not have the programming experience to understand what the code is doing, but when you show them the visual representation of the workflow, they can for sure understand how the system is going to behave. And you also get a lot of the reporting and tracing out of the box and retrying as well. And you have more controls around the error handling and all that when you have more control around the timeout for the entire workflow. And the trade-off here is with cost. Step function is one of the most expensive services you will find on AWS. You pay for state transition, so every time you go from one state to another inside your workflow, you pay for that, and you pay, I think, a total of about $25 per million transactions, which is about order of magnitude more expensive than what you pay for the Lambda invocations themselves. Which is why I typically reserve the use of step functions for those business-critical workflows, where the actual cost for robustness and all of that pays for itself, especially for things like payment workflows where you're making sure that you actually get paid. So it's worth paying a bit of premium to make sure those payment systems are really robust. Also, as you're processing these different events and you're executing your workflow, if you're also making state changes, then don't forget to publish them back into the stream as events so that other systems can react to those state changes and events and that has happened inside your workflow. And one question people ask me all the time is, well, we have all these different functions. How do you organize them into GitHub repos? Do you have one repo per function, so you end up with a gazillion number of GitHub repos? Well, absolutely not. There's no way you're going to be able to scale your mind to manage all these different functions when you've got one function per repo. Well, do you go to the other extreme and have a monorepo where everything is stored inside the same GitHub repo? There are some pros and cons to this particular approach, which are covered in more detail in this particular blog post. But But the approach that I tend to settle on is having one repo per microservice. And when I look at the Hubble social network and I draw a little quick mind map of all the different things we have a bunch of different features, such as the timeline, like you will find with other social networks, like Twitter, timeline, and so on. And also, you will have other things such as suggestions, chat, and so on, that evolve around a number of different entities in the platform, such as users, posts, brand, location, relationships, and so on. And these different entities and different features are a good starting point for you to identify the bounded context within your domain so that you can then start to break them out into individual microservices. And for each of these microservices, you can choose the most appropriate technology to implement the API as well as the database. For example, for querying relationships, it's far more efficient for me to do that using a graph database such as Neo4j compared to using, say, like a document store. And once I've identified my bounded context, I can start to break apart my monolith into as many microservices. Each microservice will have its own repo that includes all the Lambda functions that have to work together to implement that particular microservice, along with any resources that it needs and owns on its own. And every microservice will have its own CI/CD pipeline, and that all the functions are deployed together as a single stack every time you update something. And this is where we can use the strangler pattern to gradually and incrementally take apart our big monolith and then break them up into many small microservices. And we started that by identifying part of the application that's less critical, so that we get have a chance to try out this new technology while also mitigating the risk in terms of we actually break something. So we started with search, and at the time when I joined the app, they already have a search feature. It just didn't work very well because everything was built on top of a big regex query against MongoDB, which just didn't scale even to the point of supporting a couple 100,000 users in the database. So one of the first things we did, remember, was that we make sure our monolith is publishing state changes as events into a Kinesis stream so that we can subscribe a Lambda function to listen to the events in that stream. And whenever we see a user creating a profile or updating his profile, and then we can then update a search index in the Amazon's cloud search, so that we have always reflecting the most up-to-date information about the user. And then we can have an API in front of that with API Gateway and Lambda, so that we give you a search API that allows you to search the user by first name, last name, username, and we can implement the fuzzy search. So we can implement custom ranking algorithms based on how prominent the user is, so that someone with, say, 10,000 followers with the surface up high up in the results compared to someone who had just got 10 followers. And as part of our migration pattern, every time we build a new microservice, replace existing features in the monolith, we will run them side by side. And then as part of the process, of deployment process, we also make sure that we will proxy the request to the monolith endpoint to the new microservice, so that the client doesn't have to update until such a time that we are confident the new system is working correctly, is performing better. Then we can ask the client teams to then update on their side to use the new APIs directly. At the time, we also didn't have a BI pipeline to speak of, so we went about investigating what solutions available. And at the time, we were using a platform called the Mixpanel. And for some unknown reason, we signed up to the most expensive contract at Hive, which is about $3,000 per month, even though we barely have any data to justify that kind of expense. And the bigger problem that we have is that our Mixpanel is great for tracking sort of generic app events, people opening an app, closing, and so on, but it doesn't understand our domains. Specifically, it doesn't understand our social graph. A lot of the things that we actually want to query, so that we want to run from our BI, is around the social graph. How many users join the platform and follow Tiny Temper because Tiny Temper just joined? How many of them likes music, who may also be interested because some other musician has just joined our platform? And also, it has got this JavaScript-based query language, which is great for engineers, but it's not so great for our BI analyst, who comes from a SQL background. So since we have all the events, everything that's happening in the system going to a stream, so we can subscribe another Lambda function to just funnel and forward all events that we're collecting to Google BigQuery, which is a BI platform that's designed to handle exabyte-sized data sets and still return results to queries in seconds. And the first implementation, this BI pipeline took several iterations, but the first implementation took one developer just 2 days from having that initial discussion to having something running in production. And our BI analyst at the time, who just joined us from Skype, came to us afterwards and said that, no, Jesus, guys, nothing ever got done this fast as Skype, which is, of course, no offense to Skype, but it all goes back to the point I was trying to say earlier, that the lead time to someone saying thank you because you've delivered some value is a very important metric, and it's one that we should optimize ourselves towards. And as I mentioned, that the cost wasn't the primary driver for us doing any of this work, but again, we found some really healthy dose of cost saving there, because based on the amount of data, with BigQuery, you only pay for data, you only pay for it for the amount of data that you query and process. And based on the amount of data that we actually had, we were paying average about a couple of cents per month for BigQuery compared to what we are doing with Mixpanel, where we're paying a flat subscription fee for $3,000 per month. And whilst we also, at the same time, we also get a lot more capabilities after the whole process as well with the new system. And since then, Amazon also launched its own competitive service to Google BigQuery called Athena. And nowadays, if I were to do this again, I would definitely use Athena instead. But the whole system setup is still very much the same, where I have Kinesis as my sink for all events that are recorded from the system. And then I connect it to Amazon Kinesis Firehose stream, which allows me to batch all these events into large chunks and then put them into an S3 bucket. And from then on, I can set up a crawler in the AWS Glue to scan the data I have in my bucket, work out a schema, and then turn them into a table in Amazon Athena so that I can easily write query using SQL syntax to query all this BI data that I have. And on top of that, if I want to create a BI dashboard, I can also do that very, very easily by writing a few Athena queries and then type and then connect and then create the widgets in the AWS QuickSight to create a nice-looking dashboard. And one of the best things about this is that all of these things can just be done without having to write a single line of custom code myself. It's just a few infrastructure as code configurations. And also, I only pay for them when I use them. All the components you see on the screen here are pay-per-use, so when you don't use them at all, you don't pay for them, which is great. So now we've got the capability of tracking user actions and really quickly turn them into business insight using a number of different AWS resources and connecting them together using just a bit of a CloudFormation template or Terraform or whatever that you actually want to use. And we can do that in a very cost-efficient way. And from then on, we became more comfortable in terms of writing Lambda functions, testing them, deploying them, and also running and managing them in production. So we started to look at more critical aspects of a system as we started to need to develop features on, say, the timeline, whereby we have something very similar to what you find on Twitter timeline or Facebook feeds and so on. The problem that we have with the implementation was that it kind of just didn't work. At least not according to the way that the product team wanted it to work, and it was over-engineered as well. How over-engineered? Well, for the system to work, we have to write all these JavaScript modules, and we have to name them in the numeric order, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and so on. And that's the only way the whole system will work. And of course, we couldn't understand how the system is doing when none of the modules have got the names that make any sense. And the team that built this has left, and they couldn't debug the system either, which is, I guess, when you look at it, it's just no surprise. And also, the system just didn't scale very well. So around that time, new CTO came in, realized what a mess the things were, so he pretty much just fired everybody else, everybody that was involved with the whole old system. And so I came in with some other people, and we have no one that we can ask, why was this built this particular way? So we ended up sitting down with the product team to understand what they really wanted from this particular feature, and we went about rebuilding everything and re-architecting everything from the ground up by, again, consuming events that are being published by our legacy system as events into our streams. And in this case, when someone posts a new content, we can trigger a Lambda function to say, okay, now I need to distribute your content to your followers by first asking some relationship API, okay, who are Yan's followers, and then I'm going to group them into batches of, say, I think 1,000, and then for every batch, publish a message into SNS topic so that I can trigger another Lambda function who will then take my new content and add it to my followers feed, which is stored as a sorted set in Redis. And the reason why we proxy through, in this case, the SNS topic, is that when you have a Lambda function that reacts to events that are being triggered by SNS, you get 2 retries out of the box, and you also get delta queue support out of the box as well with a single configuration. And in this particular case, what you find is that with pretty much all social networks, you're going to find about 90–95% of your users will have very few followers, but then there's about 5–10% who will have many, many followers, such as Emily in our case, or any sort of famous person on Twitter will have a million followers. So what you want to optimize here is the worst case performance. In case something does go wrong, you don't want to retry and then fetch another million users from the database for this particular user who just creating new content. So this allows us to limit the retries, the blast radius, to just about 1,000 followers. And once we have the data in Redis, we can then put an API in front of that using API Gateway and Lambda, and the client, again, can talk to the new API when they're ready, but until we are open, we're happy to transfer all traffics to a new system. We will do some proxy on the legacy endpoints as well, so that older clients will still benefit from the new implementation. In this case, we've got a bunch of different Lambda functions that are doing background processing, and then we've got some Lambda functions that are doing that are serving user requests through APIs. It doesn't matter the fact that they have different responsibilities, but they all have to work together as a single microservice, so they all go into the same repo, and they all get deployed together along with the queues and topics and so on. And like other social networks, we also have a recommendation feature whereby you can go there and find people that you should follow. The platform recommends you to follow X, Y, and Z. Again, the problem that we have with this feature was that it just kind of didn't work. Because when I look into the code, what it was doing was it was returning the first 30 users in the database by creation time. Which as a recommendation feature, I guess, is rather rudimentary, and it's just... So, as you can imagine, we went about improving this feature by rebuilding it again using serverless technologies. And since we have all these events of everything that's happening in the system already being streamed live to Google BigQuery, and we can run a query against Google BigQuery for all this data and get answer back in a few seconds. So what I did as the first step was I created a cron job, in this case inside CloudWatch events, that would trigger this Lambda function, say, every hour. And this function will run the query against Google BigQuery to find out who are the people that are currently trending on our platform based on a scoring system that takes into account, say, how many people has liked your content, and then give a score to those likes, and how many people that followed you, and give a score to those follows. But then they have a time decay so that someone that followed you, say, in the last hour, has more weight compared to someone who followed you, say, yesterday. And once we figured out who are the trending users on the platform, we put them into a DynamoDB table, which we can then use API and Lambda to surface as a trending API for the client to find out who are the trending users. And anytime someone follows someone or unfollows someone, we also capture those relationship changes, and we store them inside a social graph in the graph database. As I mentioned before, we use the Neo4j. In this case, we use the particular service called GrapheneDB, which offers Neo4j as a hosted service, because again, we don't want to be managing servers. We want to be building business features and creating value for customers. In this case, once we have those social graphs stored in the graph database, we can create another API to then say, please find me people that I should follow based on my social graph, so find me the second or third degree connection. So those are people that are followed by the people that I follow, or the people that follow me, and so on and so forth. And in this case, I also updated the legacy endpoint, so instead of returning the first 30 people in the database by creation time, I would call these 2 new APIs. get the results together, do some randomization, and then return you a list of people that you might actually be interested to follow. And the nice thing about all of this is that it was pretty much done in one day because I had some trouble sleeping, so I decided to get up and do some work. Probably not the most healthy lifestyle. I've changed since then. So as we find ourselves migrating all these things, the system over to serverless one at a time, and the whole process took about 6 months, well, less than 6 months with a small team. We also found that our system became more scalable and also scales a lot faster. Because with EC2, you can find that, okay, it's all well and good, you got auto scaling, but to get a new server up and running and the serving requests behind your load balancer, it's probably going to take you 10, 15 minutes. Whereas with Lambda, it scales automatically, and you can scale very, very quickly as well. And since we had a lot of spare capacity just sitting there waiting to handle some unpredictable spikes, so with serverless, we only pay for them when they run. So all this downtime that we used to pay for, gone. So we also find that our system is a lot cheaper to run. And also with Lambda, every time you deploy your function, it's deployed to 3 data centers just out of the box. So again, I don't have to pay for the actual redundancy, whereas before, I would have to run EC2 server in 3 different data centers just so that in case one goes down, my system is still up and running. And because AWS is now looking after the security of the network, the firewall, the OS itself, it also makes my system more secure. and where was I? Right, my system that's more secure. And from the DevOps side of things as well, I get all this blue-green deployment out of the box. I deploy my function. Automatically, AWS is going to take care of getting rid of the old code and then route all new requests to the new code and then getting rid of all the resources that was running the old version of my code without me having to do anything. You just get them out of the box. You get auto-scaling. When there's more traffic coming in, AWS is going to create more resources to run my code. And also, you get multi-AZ out of the box, which means that a lot of things that I used to have to do myself, in fact, I spent most of my career doing all these things by hand, is now being done by someone who's smarter and better at this than I am. So that I can focus on my energy and my time on doing the things that only I can do for my customers, which is taking all these great ideas that the product team has and making them a reality and shipping them so that our customers can benefit. And that's, in a nutshell, is why we decided to do this migration to serverless to be able to deliver value better, quicker, better user experience to our customers and to deliver value faster and to be more efficient in terms of how we spend money on AWS. So with that, thank you guys very much for your time, and I hope you guys enjoy lunch. And if you've got any more questions, feel free to come and grab me.